Okay, so I'd like to welcome everyone to, this is actually our last distinguished GCSE seminar of the semester. And very pleased to have Professor Dongbin Xiu visiting from the Department of Mathematics at Ohio State. Dongbin is an old friend and it's really a pleasure to welcome him back. Dongbin did his PhD in applied mathematics at Brown and was on the faculty of Purdue University for several years and then moved to the University of Utah and then most recently to Ohio State. Where he's also became department head and done lots of exciting things. But more fundamentally, Dongbin has really been a pioneer in uncertainty quantification, and many of you are probably already quite familiar with his work, and has more recently started getting into work in digital twins and surrogate modeling, deep learning, and a lot of cool things at the intersection of machine learning and scientific computing. Along the way, Dongbin's won a number of awards. He's a fellow of SIAM, won an NSF Career Award, and is currently editor-in-chief of the Journal of Computational Physics, among various other journals. And yeah, it's been doing a lot of exciting work, and we're very excited to learn about things. Welcome back.
Thank you, Yusuf, for the kind introduction. Yusuf also a new SIAM fellow. Know Yusuf for a long time, so very glad to be here to visit in a more official capacity. Also very glad to have this opportunity to share some of our research. So the theme of the research is most, it doesn't show up. Okay, the pointer. Oh, I forgot. Okay, on data-driven modeling, I did throw in a more trendy term, digital twins, because this is one of our current ongoing projects. It's also where we found the data-driven modeling method we have been developing in the last 6-7 years become very useful in this context. So I would just share with you how this can be used. So I would first like to really need to acknowledge all my co-authors. These are most of the current and the former group members. The blue colors are the former ones. They have left the group. These are former, and there's a graduate student and the postdocs who have at least have one paper published in the work I will be talking about. So without them, there's a group of very talented, hardworking individuals. Without them, none of this is possible. So I feel I must acknowledge their contribution to this work. So this still works. Pointer doesn't work. Anyway, I just have one slide motivation on why we want to do data-driven modeling. This used to be the motivation for uncertainty quantification, especially for model form uncertainty. The idea is that our traditional modeling techniques, which usually requires us to throw in more and more physics, adding more and more terms, mathematically or whatever from intuition into our big model, we have more or less reached the point of diminishing return in the sense that the model are getting increasingly more complex, but what we get out of that, the profit, the gain is unclear, right? That the model can be 10, 100 times more expensive to simulate. At the end of the day, you get this kind of prediction that's wildly different. How can we make sense out of this? Does all this effort make any significant difference is unclear. So that's the motivation for this. And let me, from this very complex picture and back to a very simple setting, let's focus on dynamic systems. This will be the theme of this talk, even though the method we'll be discussing really also work with PDEs, not just ODEs, with some twists here and there, but I will just focus on dynamic system. And this is another motivation of data-driven modeling. So just to emphasize, most of the modeling, they are data-driven in the first place. So we usually see some kind of observation data. In this case, will be a time history of this predator-prey data. This is a fairly well-known one you can find on the web. And based on this, we design some kind of interaction, physical intuition, mathematical motivation. We have some nice, good-looking equations. These are our mathematical models. Right? So from this, we try to analyze and try to understand the system from which we are interested in the first place. I do want to make a point here, even for simple systems like this, in today's world, there's no such thing as a mathematical model. The model at the end of the day is a piece of software. right? So we have to, most equations will not be able to solve analytically, so we rely on numerical tools. This is a whole discipline of scientific computing, right? So, and we discretize the model, eventually we implement them in a discrete manner, and that's, for all practical purpose, our model, right? They are all discrete. And hopefully this provides a good insight for us to understand the underlying system. However, again, like I mentioned earlier, what if the models are not sufficient? For example, even in this case, what we have, the model prediction of very nice smooth curves with this phenomena, but we know what motivated us in the first place doesn't really look like this, right? So there are subtle things here and there we miss. Sometimes we're okay with this sort of approximation, sometimes we're not. If we try to get really, really accurate with the physical modeling, and then we can say, you know what, this is a good mathematical model, but it doesn't truly reflect this particular physics phenomena, especially this particular one. I will speak more about this, especially in terms of digital twins. And then we say the model is not accurate, not sufficiently accurate, but that we have enough data, especially in today's world with more and more data. So the idea is that can we use data to go one step, have a discrete model that we can use for prediction and for analysis. So that's the whole thing with data-driven modeling. We try to create this discrete model without bypass our brain power, which we realize it's kind of limited, right? So that's the motivation of that. So having said this, let me have this in a simple setup for this talk. Let's assume we have time history data. They just like time history, right? So, and we represent some kind of physical phenomena, dynamic system. We don't know. If we have the equation, by the way, I want to make a point that if you have the well-defined equation you're happy with, please, by all means, go ahead and solve them by your standard method, Runge-Kutta, anything. Most likely they'll be better than any machine learning method. All right, but anyways, here, let's assume we don't have equation, but we have time history data. Here, we just say these are just like one piece of trajectory, one piece of trajectory. I do highlight a few chunk of bursts here, which will come into play later and later, because the method we rely upon really just needs bursts of data, right? So from long trajectory data, you can pull a lot of bursts out of this. And if, again, every dot here represents a state, it's a vector, but if your data is a PD solver, then they can be an entire snapshot of field. So in which case, the vector would be much higher dimension, depending on how many grid points you have in the field. So our idea that without having an equation, we would like to use this trajectory data to come up with a model in essence, like a time stepper, like a Runge-Kutta Olaf forward kind of thing, that's such that we can march forward in time, and then given certain initial condition, our model, the discrete model, would produce a very good approximation to the truth as if we have the equation. Again, like I said, if you have the equation, you will discretize the equation, you will have exactly this kind of discrete model. And here we try to, without the equation, use data to come up with this discrete model. I do want to emphasize here, in our model destruction, we do not have time explicitly in here because that would give us significant restriction on how model can predict into the future. The key is for long-term prediction, way beyond what you can observe. All right, so that's the key idea. Having said that, I will speak about this so-called flow map learning. And why it's called flow map learning is from a very simple concept from chapter 2 of any ODE book. If we consider an autonomous system, right? So the autonomous system, and let's say we don't know the equation, but we try to recover that. By the way, there's a whole line of equations, so-called equation discovery/recovery work, try to come up with some kind of analytical form of right-hand side by some, sparse method or all kinds of things. Here we do not. We do not try to come up with analytical representation of right-hand side. As I said, everything we construct is a discrete. It's in a piece of computer software. So what we try to approximate so-called the flow map. Mathematically speaking, flow map is just a mapping between solution between two states. Right? If I know solution, the relation at one time t0 and the solution at different time is controlled by this mapping called flow, and it's RD to RD, D being the dimension of the state variable. And that's knowing the flow, the flow map is mathematically equivalent as if knowing the right-hand side. It's just governs the entire solution behavior. So from here, we say, what if I look at, from my trajectory measurement, I look at just two states separated by 1 time-step delta t. All right, so, and the flow map, but it's the same flow map parameterized by the time difference. For autonomous system, only time difference matters. Time doesn't really matter. So anything along the trajectory separating by 1 time-step is controlled, is determined by this flow map, is nothing but RD to RD map. Right, so that's the whole idea. This, so far, everything is analytical. There's no approximation. So from here, that's our idea of how to construct with a model for this. So again, now I say I have this autonomous system. If I have data of all my state variables in the trajectory, I'm going to look and say, I don't know the equation. So I do not know this, but I have all this data. We are going to look at X, all the solution, the measurement data, X state variable separated by 1 time-step. I'm going to call X1, X2. They are labeled pairs, right? So you can think X1 being the initial condition, X2 is the solution of my unknown PD by ODE by 1 time-step. This is the ending condition, right? So this is that, and they are characterized by this mapping. We don't know the mapping since we don't have the equation, but now we know the mapping is nothing but RD to RD. Now I have lots of these pairs, this being the input, this being the output. We turn this into nothing but a nonlinear, or nothing but a regression problem. I say we're going to find an operator, in fact, a function n that's as an approximation to that, it's RD to RD. We're going to put all this labeled pair x1 in here. We're going to minimize the loss at x2. And using the data, it's nothing but a regression problem. If you so decide to do a polynomial Gaussian process radial basis, you're faced with linear regression problem, which can be solved very fast. And if you so decide to use neural network to represent this n, you're dealing with a nonlinear regression, but at the end of the day, it's a regression problem. For as long as the dimensionality is RD to RD being this of x is not very high, I do say, please do polynomial, it will kill the problem to machine accuracy very fast. We do use a lot of neural network in this talk simply because a lot of problems we deal with, x is of higher dimension. For polynomial, for example, I cannot do anything beyond 5, 6, or 10 dimension, but often, especially for PD work, the dimension will be very high. Neural network does give us a way to do high dimensional approximation with available package. We'll go to TensorFlow Keras, we do Adam, that kind of thing. So once we finish this this regression problem, you fix this n, and now this gives us nothing but a time stepper. So given any initial condition, I can iterate it much forward in time. I can try to predict the future. So that's the whole idea before the flow map for fully observed system. But the biggest problem, one problem is that this all nice is that in many cases, it's hard to observe every state variable. So this is one major advancement we made along this line of approach. What if I only observe partially system? So again, we have a dynamic system we don't know in the first place, but even for the state variable, I only see part of it, z. We call this observables. And for w, I have no idea what they are. For all practical purposes, we don't even know that exists maybe. The ultimate example would be some kind of weather forecasting. Who knows if there is a perfect model for weather forecast for certain things? Nobody knows how many variables there are. Maybe there are 10,000, maybe there are 1 million variables. But at the end of the day, maybe you can just observe temperature, pressure, a few variables, density, the wind speed, and the rest variable we don't know. We have no data. We don't know if it exists. We don't even know the true dimensionality of x, but we observe what we observe. The d is what we have. So the question is that if we have enough observation of z, can we come up with a model to predict z only, without knowing anything else, right? So mathematically speaking, this is possible. There's a very well-known Morris-Zwanzig formula, which we use here as motivation. Morris-Zwanzig says a sort of dynamic system for the observed variable z does exist. It looks like this term, this is a Markovian term. This is some very sort of unfriendly integral, which is a memory term here, and provides some initial condition with as the noise. She does exist, and it's an equality. This is analytically derived. The problem is that it's sort of like existence theorem. Doesn't tell us anything how to do anything. So doesn't tell us what memory kernel K should be, doesn't tell us what R should be. So we cannot solve this. By the way, there has been an active research field to try to come up with some kind of approximation for the memory kernel here, if we know the system in the first place, the little f. Here, we don't know this in the first place, so any attempt to come up with something here is totally pointless. So, but here we use this as a motivation. Why? So let's just look at this term. So if I want to understand the system behavior at t, which is the current time, this memory kernel says I need to trace back from s equals 0 to s equals t, so t minus, so this is the current time. I need to trace all the way back to the beginning of everything. So that's what the memory term tells us. We're going to make two very mild assumptions. The first one is we say the memory is finite. So in the sense that in order to understand the current and the future at here, I don't need to trace all the way back to the beginning of the universe. I can trace back to a certain fixed amount of time, and that's it. Anything happened before that is irrelevant, has minimum impact on the current state, which is kind of true if you think of any system. You cannot just say the dynamic system, it doesn't depend on everything from the universe is created. For weather forecasting, for example, climate, you can trace back 7 days in the history, and that's about it. Anything happened 2 years ago, they are irrelevant. So we just say, this integral I can truncate in this with very small error, even maybe 0 error. So this is TM is what we're going to call the memory term. This will come up over and over. The second is that now that we focus on integral of a fixed length, if this memory remains fixed over time, now this fixed integral, I say, okay, if I have a fixed integral, I have a quadrature rule, I can approximate it, right? So if it exists, a rule that based on nothing but the solution state within this interval, I can have a good approximation with very small error. If I know the integrand, I can actually literally write down trapezoidal rule, whatever rule you want, but here we don't know. But all we need is that I need this existent. That's all we need, right? So fine. Now, after having these two assumptions, we literally translate this into an approximation with finite memory, and then within finite memory, I can do a sort of quadruple approximation, and they would take on this form I would call Tn, the current time, right? So this Tn, and this would depend on the state at the current time. This would depend on states, not only current time, but a few steps back in the memory, depending on how much memory, how long this is. Again, the problem is that I don't know these terms, but I do know they exist. Since I don't know these terms, they're just lumped into one big unknown that involves the solution state at the current state and a few in the past with the memory length, a few terms. It's one big unknown function. I'm going to lump this into this. So in order to know the future state, I need to know its current state and some terms back in the memory state. There is an unknown function for this. Again, we don't know that, but this is where, similar as before, we can come, if we have enough data, we can turn this around to be a regression problem, except now the input is much higher dimension. The dimension would be depending on how many things are in the memory term, and the dimensionality of each variable, right? And then I just map into the future. Again, it's a regression problem, it's function approximation. If you have enough measurement data, that's when the bursts come into play. You can feed everything in here and try to come up with the approximation for this. And if so decide to use neural network, this will be an illustration. So for example, if I decide for a certain phenomena, I observe few variables, I need 2 in the memory state. So then it requires you to have your measurement data to have at least 4 consecutive entries. You would put 3 in your input, 1 to the future. Then you create them. Then you do a lots of this. You have lots of these bursts feed into a 3-to-1 map, and you minimize your mean square loss. At the end of the day, you come up with a sort of neural network or whatever, or other approximator that gives you a 3-to-1 map, and that will give you this kind of time matching scheme would be like a multi-step matching, and to predict the future. If you have 3 initial conditions, you can keep marching forward in time to predict the future, right? And the problem is that the slight issue here, this isn't necessarily 3-to-1 mapping, right? So what this is an example if I have 2 memory terms. Z itself is a vector. What if Z had 10 variables, 10 dimensions, then this would be a 30 to 10 dimension mapping, right? So this is where neural network becomes more useful, as I said, it become a very flexible high dimensional approximator. We can just go ahead and use 30 to 10 dimension mapping is going to be very difficult to do with polynomial or Gaussian process, right? So let me show you some examples. The first one is a linear system equation. So we come up with a sort of arbitrary linear system equation with A, and the X has 20 state variables, so 20 vectors. A has 400 entries, 40 by 20 by 20. We pretend that we split X into first 10 component, second 10 component. We pretend that we never see the second state. We have measurement data of the first 10 state, and we can try to derive a model for the first 10 component. That's it. So if you split this equation here, you realize this is impossible, right? Because the first 10 state variable depends on the rest of them. They are coupled together. But with this, it's possible now to derive a dynamic model only depends on P. Doesn't require you to know anything of Q. In fact, in this example, the neural network has no idea there are 10 missing variables. It could be one missing variable or could be a million missing variable. It doesn't really matter. So after trial and error, we tested this thing. We realized in this problem, we only need a memory 0.6. From now on, all the time in this talk will be non-dimensional time, but let's use seconds, so it's sort of more meaningful, right? So the memory is 0.6 seconds, so we will pull off a lot of random initial 0.6 length of chunks. And we create a neural net model from this with memory mapping. And this will be a validation test with some initial condition given for the 10 variables. And we march forward in time to up to 150, way beyond your observation data 0.6, right? So, and you can see here the true state and the neural net prediction of X3, X6, they are right on top of each other. Again, like I said, we really emphasize long-term prediction. Short-term prediction is good, but long-term is where things become difficult. You can do this with...
That's about 0.6 though?
I believe this one, 0.05, we have 30 steps. So is it 30 or... There are 30, I think, 0.02, there are 30 steps. Yeah, so it's a 30 steps, 10 states. So it will be 300 input mapped to 10 states, 310 mapping. This would be, so 30 steps in the memory. Every step has 10 variables, so 30. So, okay.
I don't value this negative real part.
So good question. So when we come up with the testing, we play with A, in such a way that dynamics is interesting. So they don't decay to zero or they just blow up. So you see like this, there's oscillator in some manner. It's a testing case. If you give arbitrary A, you can have some wild behavior. If they blow up, it's hard to test error. If they go to zero, it's even harder to test error. Your error is zero, it looks good, but it doesn't show up. So we create this purposely, play with this number to get this testing case. It's all the numbers are published online. You can try this example. So this is just show you it also works for nonlinear problem. Turns out this is a very popular problem for other literature. So you can do Lorentz 63, for example. We pretend we only see X and Y. We don't see Z whatsoever. So we're going to use X, Y with a little bit of memory. And the 0.1 is the memory length. I think this all has 20 steps in there. And we predict long-term behavior of X, Y only. There's no Z here. So it's literally sort of two-dimensional model. And you can see the phase portrait. And this is up to prediction up to 100 seconds. Right? So from 0.1 measurement memory. And this is for reference, this is, the three-dimensional true thing phase portrait project onto 2D. They look reasonably close. And you can do this qualitative measurement of how chaotic the system is, all this correlation length, approximate entropy, Lyapunov exponent, they all look reasonably close. This system is so easy to train because you're not requiring pointwise error for the chaotic system. So qualitatively, it's very easy to train this thing actually to get accuracy. The linear system example turns out to be, this one is the most difficult for us to train high accuracy. But at the end of the day, you just need to train this really, really hard. Okay, we drive things with lots of tens of usually at 20,000 epoch with very low loss anyway. We push this a little bit further. I can do high-dimensional chaotic system. This Lorentz 96 is 40-dimensional, 40-state variable. Let's pretend we only have data for x1 to 3, the first 3 ones. And with memory length 0.1, we can create a closed model for x1 to 3 only. We march forward to t equals 500. You see this is, again, reasonably close to chaotic as the truth in 3-dimensional space. You look like the invariant measure of the neural network model that produced this thing or the truth, this is reasonably close. Again, it's chaotic system, so we don't ask too much of this. I will just brush this, really go through quickly. You can apply the same principle to PD. Like I said, in PD, your measurement data would be a bigger vector, right? So there are intricacies on how to enforce regularity in space. I don't want to go through too much of that because I want to focus on dynamic system. You can also do 2-dimensional things. It works. This will be example that it's a couple system, but we only observe V as a vector, only one component, one variable. And you can, with memory, you can march forward in time, have a self-closed system for V and V only, not knowing W. They look reasonably close. These are all in different papers. I do want to just focus on dynamic system in the sense that I want to talk how this become useful for digital twins. All right. So, but just before that, I want to have a quick summary that if you have an unknown dynamic system, if you know your data, the trajectory data is all the state variable, so they can be close, it's very simple. Just put immediate pairs. All right. So you can put a lot. If you have a trajectory, you can get a lot of this data, right? So then that just become very simple regression problem. If you know your observation data are not the whole state. All right, so you would need a memory, then you need longer trajectory. So the mapping would require you to this many to up to final state. So it depends on how much memory you have. This is a simplified case of this. This will be 0 memory. This will have more memory. And after training this, you have a recursive model like multi-step method. You need a little bit more as initial condition to prediction. The question may be that how do you decide the memory? Which is the way we decide is this. If we don't know how much memory the length should be, we always start with small one. Right? We train the model, we look at the prediction. If we have a reference state, it's easy. If it's off, we know. But if we don't have reference solution, we just predict the prediction. Then we increase the memory length, we double it. We train another model, we look at the prediction. Are they close? At some point, as we keep increasing memory length, when the solution stabilizes or converge, we say we stop there. So the key is to use shorter memory as much as possible. But if too short, you're going to miss your dynamic completely. But so you sufficient memory, but as short as possible. Why? There are 2 reasons. One is simple. It's computational cost, right? So if you have too many memories, your dimension is higher input. You have bigger networks. It's difficult to train. But the more important one is, mathematically speaking, you can have the longer the memory, the better, because the past would have no impact. The problem is that, for example, here, if Z is fully observed, I know if I don't need the memory, but I introduce 2 extra memory. You're not making anything wrong. Mathematically is all correct. But numerically, if these two should have 0 impact to the future, that means in your network training, all these weights have 0 weight. For any student who train network, you will never get 0 weight. You get 10 to minus 6, 10 to minus 7. You get lots of 10 to minus 6 and 7 in the connection. It adds up to a very bad instability numerically. So you really want to keep your memory, when they're sufficient, stop there. Don't go too far. You were introducing undesirable numerical artifact. Okay. So with this, I want to switch gear to show how this can be applied to digital twin. This really is our current work funded by the Muri project that's funded by the Air Force. This is our team. At Stanford, most of the computational engineers, they're focused on modeling part. We at Ohio State are on the data-driven modeling and sort of reinforced learning for control. At Caltech, Huma Owadi focused on complex system modeling, identification of different components, and Boris Kramer and UC San Diego focuses on reduced order modeling and also control with more classical approach. So it's very well-oiled team. We work very efficiently together. So I don't know how much exposure everyone here has to digital twin. I don't want to spend too much time on that. just give you a quick word. What is digital twin? And these are just these are stock photo on the web, and a few random quotes. I didn't even bother finding the origin. They all sound similar. Right? So, from this random description, you can sort of get the idea what digital twin is. So there is a physical entity, like in this photo. And then there's a digital representation. Digital twin really is a digital or virtual representation of this physical twin, what we call. And the key here is also your digital representation need to be synchronized with the physical thing in real time, all the time. So that's then the goal with having a digital twin is to allow us to conduct analysis and also optimization and control for the physical twin. So that's the whole idea that's a basic idea behind digital twin. There is no fixed definition for digital twins. There are a few well-accepted facts. One is that the idea was really conceptualized by Michael Greaves in the 90s, and John Vickers, who works at NASA, is a collaborator of Michael Greaves, officially termed digital twin in the NASA roadmap report in 2010. I recently had a discussion with Michael Greaves and John Vickers separately. John Vickers actually said when they first came out with the idea, they had a very, very long name for that. Then they decided it wouldn't stick. I think they were right. Digital twins really sticks. So like I said, digital twin has three critical component that need to be a physical thing, there need to be a digital representation, but there also need to be a bidirectional data exchange. So we call this P2D, means that the digital twin need to be synchronized with the physical thing. So whenever the physical twin undergoing environmental change or state change, this need to be reflect in your digital twin. So that requires a lot of parameter estimation, all kinds of things, right? Then the other direction is D2B, digital to physical. That's when digital twin become useful because you want to apply optimal control or decision making to the physical quantity under all kinds of conditions, sometimes catastrophic, unexpected conditions, but you cannot do this in real time. But this is where digital twin becomes useful. Being a real representation of physical twin, you can play the what-if game in your computer with no real-world consequences. And once you learn all these the strategy, the control strategies under different conditions, and then when things happen in real world and physical twin, you already have a strategy you can rely upon. So that's where digital twin becomes really useful. As of today, there are very few very concrete, complete example. Despite all the motivation, all the color pictures online, nobody has a digital twin for aircraft, that kind of thing. If you're interested, there's a very good National Academy of Science report last year on the opportunities and challenges for digital twins. You're more than welcome to read. I do caution it's 400 pages. I just want to add a few, one word is that one question one may have, which certainly was the one I had when I first heard the concept, was my question was, what is this? It's just modeling, what's the difference? It's different in the sense that this is not the modeling we are used to. It's true, many of the components, research components of the digital twin have been studied independently in different fields. I list all these components. Each one of them is a very big field. All of us have worked on in this field more or less. So the question is what's new? The news is that this is a very, very specific individualized model. For example, you say, I want to do a flow simulator Navier-Stokes, you're modeling flow in the channel or something. You can do that simulation. You say, I have a model for that, but digital twin requires to model that particular channel. And at that channel change, you need to reflect that and to control that channel. So it's very individualized. I can do three-dimensional heat convection problem with my finite element code. That's all good, but then people say, I want to do a digital twin for this room and this room only. With that kind of door, with this people inside moving around, I want to have a control understanding of this. This is digital twin. It's very different. Every component has been studied, but to put them all together requires a lot of new certainly introduce a lot of new challenges on how to couple things together, how to control things together, and it's more important how to make decisions. So this is really the key here is a real-time monitoring, real-time mirroring of the thing, and you also need to update this in real time. So having said that, we have a sort of framework, conceptual framework. This is not that I will speak a little bit more in a moment on how this can be done. Okay, everything about digital twin is expensive. You can think as a very complex, dynamic PD solver with many equations and ODEs, reaction, all kinds of things. It's very expensive. How do you do control and optimization in real time? There are, of course, all kinds of things you can do with reduced order modeling, that kind of thing. What we say is that that's not enough in the sense that can get us far, but for real time, you really have to make sure things happen fast. So we sort of introduce this framework that in addition to the physical to digital synchronization direction, and also the other one, digital to physical, we introduce a digital to digital, what we call D2D self-learning part. Right? That's our framework. We call it PDDP. What happens here, everything here happens in real time. We want this, but in order to enable this happens in real time, we are going to be in virtual time, non-stop do training of things you want to accomplish. Like this can be your control strategy under different scenarios. So you can execute your digital twin under different hypothetical scenario, and you come up with the control strategy, and then hopefully you can have some kind of mapping, and then in real time when you have a new scenario, you can just go to that mapping without executing digital twin to optimize again. So that's a very high level sort of way we envision this, and that's what's built in our proposal, eventually run as a key component to get the project funded. So I will speak this to put this into a concrete framework, how this can be done in one way, right? So one way is that suppose I have a digital twin or I have a full simulation dynamic model. This is some complex PDE. We discretize it, everything is discrete, and it's a dynamic model. Again, this is what you're going to have in your computer, right? So and U is capital U is very high dimension. You have a three-dimensional simulation, you can easily have millions degree freedom. So the capital N is huge. I cannot do this in real time or understand this in real time. But the quantity of interest or things you want to control, we argue that in most cases, they are very small quantities. Right? Even if you drive an aircraft in your control state, you're just doing a few things left and right, a car left and right. So control strategy or things really matter to you are usually not your solution at every location in the field. It's just a few quantities, right? So let's focus on these quantities of interest. They are very low dimension, just a few variables. The question is, can I have a model for my quantity of interest? Just a few variables. You say, no, I cannot, because my quantity interest depends on everything in my solution field. Depends on literally, actually, this would be capital U, right? So depends on everything. I have to solve the forward problem, get to here, and understand the dynamic behavior of this. But using what I described earlier, well, this is just a small subset of things in my bigger system. Maybe with enough memory, I can learn this. That would just require us to have a lot of training data, depending on how long the memory is, to learn this mapping. If I learn this mapping, the flow mapping, I can march forward, understand my quantity interest now without knowing the entire state of my PDE solver. That's the idea. So now how do I get data of this? This is where what we call the D2D learning part. In virtual time, without using anything from real world, we're going to run my digital twin or my model, no real world data, on the hypothetical condition. In this case, let's just randomize my initial condition, randomize my parameters. I'm going to execute my full three-dimensional computation. And after this, I will collect the time history of my V. These are all well-defined forward problem. Once I collect enough data for V, I'm going to train the model on this dynamic model of V only. And then once this model is finished, I can predict my quantity of interest without going back to my full state of variables. That's the whole idea. So now this becomes sort of, you have a model, it will never be mathematical because this doesn't exist. But numerically this is possible. Let me show you one example how this can be done. This will be for a flow path cylinder. So it's a classical CFD benchmark. All right, so the full digital twin or full model in our case, we use Nectar++. It doesn't really matter. You can use Fluent. You can use other things. We didn't write our own code. Let's just put it that way. We put a mesh here. Is flow path cylinder. Flow comes from left to right. And the critical number here is Reynolds number. If anything, if my flow is not changing, the Reynolds number quantifies how fast the inflow comes. All right, so this is a typical flow path cylinder thing. At low Reynolds number, low speed, you have the periodic vortex shedding. At high Reynolds number, you still shed, but you can see the tail. There's another frequency that's sweeping the tail at higher Reynolds number. So that's the typical thing. So this example, we had about 150,000 degree freedom for my full simulation. Again, this is not going to be very useful for real time because it takes a few hours to simulate one case. So now I say, what if I only care about two things? I only care about the force on the cylinder. In this case, unless you're hardcore fluid dynamics, you don't really care about the vortex. For flow structure interaction, the force on the structure is important. So I say, I want to understand the horizontal force, which we call drag. I want to understand the vertical force, which is the lift. Now it's a vector of two. I only care about two numbers from the entire flow simulation. So I would like to construct a model for drag and lift only without flow field. That's how do we do that? Exact principle I said. Let's first generate our training data. This is a D2D learning. This will be expensive. They will happen on real time without any real world happen in virtual time, but it doesn't use any real world data. So we say we decide our range of interest for Reynolds number is between 100 to 2,000. All right, so what we can do, we can randomly sample Reynolds number here in this range. Once we sample Reynolds number, we can do a full-scale CFD simulation of time to t up to 200 with a sudden start condition. That's all, with a small time step that's required by my solver. The simulation takes about 2 to 3 hours. We cannot record anything. It's a lot of long-time simulation. So we only record the time history of these two numbers of drag and lift in this time domain. So now I'm going to pull chunks burst out of this. After testing, we realized in this case, the memory needs to be 5. So we did a lot of testing. 5 is good. So we're going to, for each this simulation, we're going to put 10 random bursts from this long 200 seconds. I'm going to put 5 seconds randomly out of this of drag and lift. 10 drugs, so that then I have 10 pieces of training data. That's it. So that's one sample. The next thing you do, rinse and repeat. I'm going to repeat this many, many times. So I can draw another Reynolds number, do another simulation. We did this 7,800 times. So at the end of the day, each simulation gives us 10 pieces of training data. We get 78,000 pieces of training data. What do they look like? This is what they look like. All right, so this is one random Reynolds number. You can do a simulation, steady state. I mean, it's not much oscillation, periodic state. This is drag and lift. At this point, there's no field. We never store any CFD field. We have no hardware space to do that. So everything here are time series. Right? So we have this rectangle represents random sample of chunk of 5 seconds. This will be all the 10 chunks we random sample from this single Reynolds number. We do two more things which are critical. One is you look at every random sample of this has starting time, ending time of separate 5, right? We're going to remove all this. Everything for us starts from 0 to 5. The real time doesn't matter, only relative matters. Right? This is fun. This is actually critical. Secondly, we're going to remove Reynolds number. So I don't really want to know what Reynolds number this is. All I see is a chunk of 5. That's all we see. All right, that's it. So this gives us 10 training data. Do what? So like I would emphasize, the actual time is not recorded. Reynolds number is not recorded. We throw them all away. All you see is this. Another sample, another Reynolds number, but much higher Reynolds number. You can see the oscillation drag lift much wild, bigger. Random sample, 10 pieces chunk, 10 burst. Again, remove all the time, everything 0 to 5, remove Reynolds number. Give me another 10 training data. Now we have 20. Repeat. At the end of the day, we would have 78,000 training data. They all look like this. This example, another 10. They all start from 0 to 5. They are all associated with some kind of Reynolds number we don't know. Okay, every one of this has a Reynolds number associated. We don't know. So now this is our training data. We decide, okay, looking at the structure of this, times that 0.1 second is enough. So we put 0.1 second. So between 5, we have 51 discrete points, right? So we put the 50 into input, the last one as output. With 78,000 of this, I train a network. I create a mapping between 100 to 2 because there are 50 for drag, 50 for lift, 100 input, and only 2 output. So in between a very simple network with 5 hidden layers, each one with 50 nodes. Feed forward, nothing fancy. You do the training, that's it. And now after training, you get a dynamic model for drag and lift without requiring anything about the flow, because the flow would be Reynolds number, where this thing start, the starting ending time, we don't know. So given an initial time series of 5 seconds of drag lift, which you can get either from some kind of simulation, or you can, in real world, maybe you can get from measurement. It doesn't require you to know the Reynolds number, doesn't require you how long this has evolved. I only need to know this is 5 seconds. Fit in here, I can keep on much forward in time for long-term prediction of whatever Reynolds number that is. I never know, but it will try to produce that dynamic behavior of this flow field. So let me show you 2 examples. This is from this Reynolds number at this starting time. Again, these are unknown. This is only benchmarking we validate. We use these 2 numbers so I can run my 2D CFD simulation so I can have a reference solution. So here are the initial 50 to start, and the circle are the full CFDs, right? So the red line is our 2D model to go. Let me see, this will be long-term drag and lift. You see the long-term prediction of this, and as you can see, go forward in time, this very simple model takes a few seconds to run. We'll capture drag and lift, the structure, the time frequency over time, right on top for the movie goes for 100 seconds later. All right, so the total prediction time is 100 seconds. Okay. You need 5 seconds to start. Let this finish. Again, the full CFD simulation takes about 3 hours, okay, to get these blue circles. Let me give another example. This will be a different Reynolds number, again, unknown to the flow map model, neural net model. But again, this actually starts from the first second. We put this time history as first second. The flow just started. The vortex setting hasn't really started yet, right? So, but the model doesn't know anything. You just see the 2 time history, drag and lift. It will start to go forward in time. This will be quite interesting because at some point it knows that it has to go to somewhere for some kind of periodic state with double, triple frequency. And this again is prediction for 100 seconds into the future beyond the 100 beyond the vertical line, which is the initial condition. So, and once again, in this case, without knowing the Reynolds number of flow, it just capture this dynamic behavior right on top of each other. Again, as I emphasize, this long-time behavior. So these are good. We can reproduce anything between Reynolds number 2000. Give you just some time history much forward in time. Just get you this. So let me show you another thing. I say, what if I want to know more about the force on the cylinder? The drag and lift 2 numbers are good, but what if I want to know the actual distribution of the force, the pressure on this? Let's look at the pressure, okay? So the pressure on the surface cylinder, luckily it's a surface it's a cylinder, so it's a periodic surface. We do exactly the same thing. We actually use the exactly same simulation, except this time now we record the surface pressure at time history in the 200. For modeling this, we try to reduce this. So in fact, it's a periodic function, right? So we write a Fourier series. We decide 30 n equals 30 is enough to capture variation. So eventually, our flow map model track the Fourier coefficient of this. So there are 61 coefficients here. 30 cosine, 31 cosine and 30 sine function, right? And it's the exact same thing, 78,000 piece of data. The difference that now the network become a lot bigger. Again, we have 50 in the input in the memory, but each one requires 61. This is 61 coefficient. So the input has 3,050 nodes for the Fourier coefficient, the history of Fourier coefficient. Output would be 61 in the future. And in between 5 hidden layers, we use fully connected. We try to reduce number of parameters. So we experiment this. This works well, right? So this is fun. And once we fit that, now we can march forward a Fourier coefficient of the pressure, which allows us to reconstruct the entire pressure distribution of the cylinder. This will again be another testing of this Reynolds number starting at 200. In fact, we run this thing at 200. Then we say, let the network to go to predict the future without this. Again, this doesn't go into network. So you will do this, and you can see this start to march forward in time. It's a very so how to read this flow comes from left to right. The blue circle is the rear part, rear of the cylinder, which is here. Theta equals 0, and diamond in the front plus minus pi. So you can see plus minus pi. They are single point, they're periodic function at left end. So the rear has obviously low pressure. The front has higher pressure. It's always like that. In between, because of vortex shedding, the pressure would oscillate. You can see the pressure actually sometimes has very fine structure. So when we use 60 Fourier mode, it really can capture the fine structure. This already up almost 100 into the future prediction. You can see the neural net prediction, which is blue, and compare the full scale thing. They are still very close of these things. I will emphasize in this case, the simulation by this model goes faster than the visualization. I mean, of course, the full simulation takes 3 hours, but this is in my time in my talk, I actually need to speed this up. Let's see. As you go to the further into the future, this is very long term, right? This is 400 seconds. You can see the difference. And but this is mostly because periodic signal eventually for long-term prediction, you always have little phase error. They accumulate. The actual function you look at, they are actually right on top of each other. The difference really is a little phase error. So anyway, at the very last frame, when it stops, you can see this maybe fairly clearly. You can see the function form are very close. It's just phase shift accumulate over time. This is inevitable for almost all numerical methods. In fact, in this case, we say this phase shift is quite good for this long-term prediction. So with this, I would like to, time is up. I would like to finish. So I talked about this so-called flow map method. It's very useful because it offers ways for direct modeling of things you want to understand without knowing anything else. You can bypass it. In fact, if you have uncertainty in between, you can completely bypass that. It can also speed up. You have a high fidelity simulation code. You can speed this up. This becomes very, very useful in the context of digital twin, as I discussed. I do want to emphasize this sort of new, if this is anything new, it has nothing to do with magic of neural network. It's all about setting things up properly. Neural net to us is nothing but an approximator that's very flexible in high dimension. None of this requires any special structures. In fact, most of them very small network. And finally, if this is, again, this sounds like something quite new, it took us several years. So it took us a good 7-8 years to reach stage and to become now, I would say, quite capable for real world problems. So with this, I would like to finish and thank you very much.
Thank you, Dongbin, for a fascinating talk. We have some time for questions.
Were there any mathematical restrictions on the underlying system dynamics so that your approach can work effectively? Like, for example, why isn't stationary or periodicity? Or would this work well on dynamic models where the underlying parameters are also time varying?
Oh, underlying parameter time varying. You're talking about non-autonomous system. Yes, it does. What we have, I didn't have time to talk about that. So we have a separate paper. We do that a lot, actually. But if what I did not talk about is this arbitrary external input, non-autonomous system. Yes, it does work well. And also with SE, we have perturbation, it works well. So yeah, well, time varying system, yes. Thank you.
In the last example, you mentioned that the sort of error accumulate for a longer time, but also somehow in the real case, there are errors that like within the system.
Right.
Your example so far didn't have that error term. But have you had sort of experience with actually sort of the real system that have a lot of measurement errors, for example?
We have not done, so this is another one way to reproduce whatever the model. So like in this model could have error, exactly, you're absolutely right. But this method would try to reproduce whatever the model gives you. That's why I said in this case, you would, did I have that? Encourage the use of high fidelity models to have smaller error. It produces whatever the data comes from the model. If your model is bad, it would do the bad job, but it will do whatever the model gives you. So that's, so yeah.
My question is about because you use a short-term memory, actually, because we want to save computation power, so we want to use just a snapshot of what has happened in the past to predict in the future. My question would be, if my dynamical system has two timing, for example, one high frequency dynamics and one low frequency dynamics, then are we going to totally lose that low frequency part?
I don't know. This is no, you don't. Example would be kind of like
There's one example that you showed the prediction for
it is for this does have two frequencies. I mean, it's not so extreme. You are talking about sort of multi-scale system. Can we lose that?
better modeling methods so that we can learn that from the data.
I cannot say for sure because we have never validated that thing. I would think it's not a problem because our data is very short term. So whatever you think of high frequency, low frequency, usually high frequency, very short thing, you like this, there's no frequency here in your initial thing. When you observe, it will develop its own frequency, but you're asking if I have an extreme case, I observe this, eventually you have two vastly different frequency. I don't know, we have not tested that. So I would think it should work, but I cannot say for sure, but yeah, I don't know. But I don't think it's difficult. It will be a deal breaker for the method, but I don't know. Without doing it, you can be surprised, so.
A related but simpler question, stepping back to like smoother dynamics, do you have any problem with forgetting? Because like for chaotic dynamics that you're showing, it's, you know, you don't need a long time scale, but for the easier smooth dynamics, I would imagine that you need a longer memory.
So that's one thing we don't know how to like a priori estimate the memory. So what's the, you ask what type of system give you the question of what type of system, what property the system has, and maybe give us some idea of the memory. We have not, I don't know if there's theory on that. We don't, so far everything done just by numerical testing. So I would say a lot of systems have surprisingly short memory. So they're not too long, but I don't, yeah, there's no theory on that. Yeah, no, yeah.
Have you tried doing long-term prediction in the more strongly turbulent setting for the vortex shedding problem, and how well do you do its statistics there?
This problem we did, that's the actual reason we still stay the Reynolds number between below 2000. Even for this, if we go to, we do have the code can go there, 5,000, 10,000. We try to avoid is that in that regime, the boundary condition need to be modified. We don't want to introduce another thing that's not our issue, but we have not tested turbulence yet. So that's for sure. But the capability, I don't know. If you have a reliable code to generate for flow path cylinder that with well accepted boundary conditions for turbulence, would love to try. You know, all these things always required to generate data. The training is same thing. So
I expect you'll always do well within the Lyapunov time, but the question is, does the auto regression application like drift the statistics over long times?
I don't know. It's unclear. We have not looked into that. So.
Any, well, we can answer on, there might be online questions, but.
Yeah, okay. Oh, yeah.
Oh, that's it.
Oh, okay.
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 Great. All right, I think we should go past the hour, so let's thank Dongbin again for passing.
All right. Thank you.